And we look.
Do some of the people coming. So too early.
16:00.
Wow, I think that we start 16:00 sharp.
We used to start sharp.
Yeah. You have speakers online and people joining online. Welcome everyone. Today we are hosting actually the visitor who's here for 3 months, Neha Singh. Neha did her PhD here and at the Observatory, and then she moved for postdoc to France, and then she moved to Spain, to Mallorca, to be exact, and she's working on evolution of binary black holes from populations 3 stars together with Tomek Bulik. The floor is yours. Man, I'm stressed.
Okay, thanks, Milena. So today I'm going to talk about the catalog that we generated for population 3 stars, essentially, why we did it and why is it necessary. So first I will talk about the current status, the special events that were detected by LIGO Virgo Kagra collaborations and why are they the motivation for this work. Then what are the prospects of detecting population 3 binary black holes with the current and the future detectors? And then the catalog that we generated, why do we need it? And the importance of the evolutionary parameters on the properties of these binaries, how do we quantify this effect? And finally, the conclusions. So I'll start with this event that was detected by LK in on 21st May 2019. So this is a special event. Why? Because first of all, the remnant of this binary was an intermediate mass black hole. And at the time of its detection, it was the most massive binary detected. The another special thing was that one of the components, the primary mass, the heavier one, the mass of that primary lies in the pair instability supernova mass gap. Now, given our understanding of how pair instability supernova works, we don't expect black holes to exist in that mass gap. Although this mass gap is not a very strict boundary, some of the analysis says from 50 to 100, some say 60 to 120 or 65 to 130. So, but essentially the primary mass here, the median being 85 solar masses, lies in this mass gap, however you define the boundary. So again, since we don't understand the formation of such black holes, there were many attempts to explain this formation. There were multiple papers after this detection which claimed that maybe it happened via hierarchical merger, maybe it was a merger of ultra dwarf galaxies, maybe it was multiple collisions of existing black holes, and so on. So for today's talk, we will concentrate on how the formation of this binary black hole was explained to be coming from first stars of the universe, the population 3 stars. So there are these papers. It's not clear very, but okay. So there are these multiple papers with groups which claim that maybe this binary was formed by the evolution of binary stars, which were the first stars of the universe. The issue with this analysis is that all these different groups had different assumptions, like different assumptions on what is the carbon oxygen nuclear reaction rate, what is the mass loss that happens along the evolution, and also on the what is the limit of this pair instability supernova, and finally what is the initial mass function assumption for such first stars of this universe. So they were able to form such a binary which looked like 1905-21, but essentially the assumptions that went into such formation were quite different. Then very recently, this another detection happened, which is the most heaviest black hole detected by the detected till date. So the total mass is about from 190 to 265 solar masses. So there are multiple speciality of this. First of all, the remnant is really massive. Each of these components are also very massive. The primary is 137 solar masses, and the secondary is 101 solar mass. That is the median value. The other thing is that both these binary have unusually high component spins, although these spin measurements have quite large error bars. So again, the question was, how can such a black hole form these heavy binaries? Because in essentially we understand that such high mass black holes cannot be easily formed by a simple stellar evolution scenario. So the concept, the idea was, can it form from the first star? So this group by Tanikawa et al., they also tried to reproduce the earlier event, 1905-21, and they repeated the analysis for this particular event. And they were able to form such a binary. The problem is, and they stated it clearly in their paper, that when they tried to form the binary 1905-21, they used the standard reaction rate for the carbon-oxygen nuclear reaction. But when they tried to form a binary which represented 231123, they had to lower this rate by 2 sigma. So they pointed out this issue that you can form such a binary with POP3 stars, but you don't know exactly how you can form it. Then the question that we are asking now is, are these the only effective parameters, the variation of which will result in the formation of such a binary? And second, if there are, we know that there are multiple parameters in addition to this, then what is the individual effect of each of these evolutionary parameters on the properties of the binary which will be formed finally? So what will be the parameters which will affect the Church mass? What will affect the separation of the binaries? What are the parameters which will affect the eccentricities of the binaries? So to start with the current status, on the left side, top plot is for the O4A sensitive binary neutron star reach for the LVK. So essentially what you can see is that during the this run O4A, the maximum reach was about 160 megaparsec. So on the lower plot, what I show is the green dot that you see here. This is the O3A sensitivity, O3 sensitivity. This is O4A. These are the ones that are supposed to happen later on. So these are the points which represents the LVK's BNS reach. The BBH reach is a bit higher. So in O4A, it was somewhere here, a redshift of 1.5 or so. So again, the detections that have been made already, on the right side, what I show is the merger rate limits, those that were estimated using these detections. So the green curve that appears, this one, is from the GWTC1, the first catalog that was made by the LBK. The blue is the second, and the red one is the third. So what I want to show here is that the rate does not decrease with the increase in number of detections that we have. It kind of shifts or maybe becomes larger in one of the axes. The x-axis is the BBH merger rate, and the y-axis is the BNH merger rate density. So what we know is, even we have so many detections, the merger rate constraints that we have large error bars. And we only probe a very small redshift with the current detections. What will happen when we go to the next generation detectors? So on the left side, you see the reach of each of the future detectors. So the green line is for ET here. So for a 3030 solar mass black hole, it can detect up to redshift almost 100. While the CE also has a similar reach. For neutron stars, the Cosmic Explorer has slightly larger detection reach compared to ET. So given these sensitivities that we have for the future detection that are expected to be there for the future detectors, you will be able to detect much heavier and binaries which are much farther in redshift. But then the question is, suppose you detect these, how many will you be able to detect? So a few years ago, we did a study to understand this scenario. Suppose you take a population of 1,000,000 binaries. So the red curve here shows what will be the merger rate density of this population at each redshift. So this red curve shows you the merger rate density of any population you assume, suppose say 1,000,000 binaries. Then the blue curve shows how many of these will you detect, because we have a detection criteria. We have to decide what we call as a detection. It has to be stronger than the noise. How strong do we need it to be? Defining this detection criteria, not all the black holes will be detected. Why? Because it may be at a wrong point in the antenna pattern. It may not generate enough SNR. So even though you have a million binaries merging at the redshift, they are not equal masses. They may not generate equal SNR because they are at a bad location. So you lose the binaries. Now the problem is, suppose out of a million binaries, you lose half of the binaries. Now you need to know where, at what redshift do you lose them? Because if you don't have that information, you cannot reconstruct the true merger rate density. The green plot here shows that if we detect these binaries and do the parameter estimation by the algorithm that we have, we will be able to correctly estimate that merger rate density. But again, it is not the true merger rate density is much farther than the true one. So the logic is we need to estimate the merger rate density of the binaries that we detected. We need to know how many we lose. We need to know where we lose it. And then you can construct the true merger rate density. So what we did is, in general, in literature, when this detection efficiency, that is how many binaries do you detect at each redshift, is estimated, that is calculated with a much simplified assumption. So either like for neutron stars, you have to assume they are equal masses. For BBHs, and you have to assume a simple distribution in the volume, cosmic volume. What we did here is we said, okay, we don't assume anything about the true population. We say whatever we detect represents the true population in chirp mass and redshift. And we assume that we only lose because we don't see them at a good orientation for the detector. So we constructed this secondary population, assuming this, making these assumptions, and then we calculated if this is a population, how many will we lose? So this is how we calculated the detection efficiency, that is number of binaries detected divided by number of binaries that were originally there in this redshift bin. So dividing this by the detected merger rate density, you can get the true merger rate density. So we were able to show that with this algorithm, even though you lose a bulk of binaries, you are still able to reconstruct the true merger rate density up till a very high redshift. These are the POP3 binaries that we did the estimation for. And this is a population independent algorithm. We also applied it for the binary neutron stars, because in binary neutron stars, you only detect about 10% of the binaries. So you lose a major chunk, but we were still able to reconstruct the merger rate density. So why is this important? Because there are multiple evolutionary parameters. If you change these parameters, you get different populations with different binary masses, different separations, different eccentricities. So essentially, they will have different merger rate densities. So if you can reconstruct these merger rate densities or the chirp mass distributions, so then you can go back and constrain the population parameters which resulted in these properties. But then to do this, you need to have a large bank of populations so that you can go in and identify which one is the correct one. So this led us to the need of a large population 3 catalog of POP3 binaries. There are multiple models which exist, but not so many. So the method, the idea that we have is we do a exhaustive parametric study of binary evolution. We identify which of the evolutionary parameters are the most important ones which affect these parameters of the binary, and then quantify this effect, like how much do they affect. So for the past few months, the catalog that we are constructing, in this catalog, what we did is we varied set of 8 parameters, and this resulted in a more than 1,000 models. So in generating this catalog, what we varied is the initial distribution of the mass, the separations, the eccentricities, how efficient is the orbital energy loss during the common envelope ejection, the fraction of mass lost during the accretion, and more also what is the remnant mass prescription. That is, whenever the core collapse supernova happens, how much massive will be the compact object which is formed. We also varied the sigma for the Higgs distribution and also how much the mass and radius changes with each time step. So for this talk, I will be talking about the 520 models which are finished and processed. So these are just the preliminary results. So here what I show is the chirp mass distribution. Let's talk about the plot on the top. The left panel shows okay, this not clear. So this is the model number. This is the chirp mass, and the color denotes how many binaries are there in that chirp mass bin for that particular model. Now this number is 10 to the power 1, so 10, this is 1, 10, 100, and so on. So here you can see that almost none of the binaries are formed given the parameters that this model had. So here you can form many more binaries, but also not so many. Most of them are here. So more than 10,000 binaries are formed for this chirp mass in these models. And just to be clear, we ran about 10 million binaries for each of these models. On the right plot, what I show is model occupancy. What I mean by this is, suppose you have a model. Does that model produce a binary of chirp mass 70, say? So then it is counted as here 1. So essentially the binary with chirp mass of 70 is predicted by 150 models out of the 500 that we had. And this one, the binaries with chirp mass between 20 to 30 are produced by more than 250 models. On the lower, but then the top panel shows a binary, all the binaries that were formed in the simulation. But then the important point to remember is not all these binaries will merge within the Hubble time. So if we have to detect them by current detectors or future detector, they had to form and merge within the Hubble time. So the lower panel shows only the binaries which are formed, which will merge within the Hubble time. So you can see the models in the lower set of this models are all gone. So they are formed, the binaries are formed, but they will not merge within the Hubble time. So essentially, if I claim that, okay, my model can form such a binary, but then there is no way that it will be the one that we detect because there is no chance of it merging within the Hubble time. So in both these cases, heavy binaries were formed, but they won't be merging. They were at least in the lower set, the binaries were very wide binaries. So you can see how the chirp mass distribution changes when we apply this cut of Hubble time. Then in this plot, it's much easier to understand the models in terms of the total mass distribution. So I show the similar uh, plots for the total mass. Here is the model number, and this is the total mass. So you can see here, whatever assumption we made, not many binaries were formed in this so-called mass gap. There were heavy binaries which were formed. So we were able to form binaries with total mass of 175 solar masses with almost 200 models. And the total model here plotted are 288. So bulk of the models produced very heavy binaries. But then if you apply the cut of how many of these will be able to merge within Hubble time, then we see that there are not so many heavy binaries which are expected to merge. Here they are all gone. So these are wide binaries which we will not be able to observe. The other point to remember is, although we generated these 500 models, we have not applied we have not taken into account the star formation rate yet. So essentially, when I'm saying the Hubble time, it starts from the very beginning and to the end. So if you apply the star formation rate, more of them will be removed from this category of what can be detected. We see that the heavy binaries, first of all, are formed by a few models, and then those models, these binaries are also very rare in those models. Then we have this eccentricity distribution. On the top plot, I show the eccentricities for binary black holes. You can see that in case of the models shown here, we can produce binaries which have very low eccentricity to high eccentricities. But in these models, the bulk of them have very high eccentricities. So this is the eccentricity distribution per model. Now, if you say which one of these will merge within Hubble time, you get this kind of plot. Why? Because the gravitational radiation formula already tells you that if the binary is highly eccentric, it will merge faster because it radiates more. So the binaries here, since they were low eccentricity binaries, they will not merge within Hubble time, although they are formed by this model. And the only ones that you will see merging are these ones. But then the point to remember is that these are the eccentricities at birth. The thing that we are interested in are will we be able to detect any eccentricity from these binaries with the future detectors. So what I'm showing here is the binary black hole eccentricity at different frequencies. The frequencies correspond to frequencies of the detection band for future detectors. So for example, 0.01 is for Tiankin, point 1 is for Disigo, 1 is for ET, and 10 is for bad ET. So what you can see here is BBH, there are many binaries which will still have eccentricities greater than zero point 0.1 and will be detectable by Tiankin and also by Disigo. Now, although this talk is about BBHs, but we also have interesting results for NSBHs. And so this is what I wanted to show also. In case of NSBHs, you have much more binaries with high eccentricities, which we will be able to detect with uh, Tianken, Disigo, and also some with probably ET if it goes by down like to 1 hertz. Now we have generated the models. The question that we had to was, if we have these models, we need to quantify what parameters are important and what is the effect of each of these parameters. So what we did is a variance analysis. Essentially, if you have a quantity, say y here, and it is a function of multiple parameters, and you want to see if you fluctuate x, each of these x's, what will be the effect of fluctuation on the final output y. So Sobol did this decomposition of this function and said that if this function is square integrable, you can write it in this manner. You can divide the function into multiple components, each of will be square integrable, and then you can find the effect of each of these input parameters and also what is the interaction between these input parameters. So essentially, what I'm trying to say is the components here, what do they physically mean? So F naught is the expectation value of the quantity that you want to see the fluctuation of. Fi, Fij, these are the interactions of the first and second three components that you have in. So for example, suppose you want to say how many students are there in the observatory, say on a given Monday, and what are the parameters that decide this attendance. How do you quantify it? That's the thing that we are trying to do. Suppose you are coming here every Monday, all of how many people are there? Now, what are the parameters that you can think of? First of all, do you have the motivation to come to the observatory? Like, I want to work from home, I have more motivation to stay at home. The second is, how far is your home from the observatory? The third one will be, is there a lecture or meeting that you want to attend? Or maybe is there a party afterwards? So these are the parameters that maybe decide, are you there in the observatory or not? So, but then, so in a way, if somebody wants, the faculty members here want to do an analysis, they can find out which parameter is the most important, which decides people to be in the observatory. So this is exactly what we did. Now the total effects, the example here says, if there are three variables, the total effect of all three variables will be the effect of the the Sobol indices that we call it here is the Sobol indices due to the first variable with the first index, the primary factor, the interaction of the first and the second variable, and the interaction of all these variables. And the value of Sobol index is always between 0 and 1. So this is the analysis that we want to do. Suppose in our case, what we did is we had variation of 8 parameters. Not all these parameters were numbers. some are prescriptions. So essentially we have an 8-dimensional grid which have prescriptions and numbers in it. Now what you do is imagine an 8-dimensional grid. You take one point. Now corresponding to this one point, there is a quantity of interest that you want to identify the fluctuation on, say chirp mass of the whatever the maximum chirp mass of that model is. So what you do is go from one grid point to another and see how much the final value fluctuates. So doing this again and again and again, and you can find out which parameter affects the final quantity the most. So for our analysis, we chose 4 that I'm showing here. Why? A is the separation of the binary. And A90 means for a given model, 90% of the binaries are within this separation value. Similarly, E90, E is the eccentricity. E90 meaning for a given model, 90% of the binaries are within this value. M max is the maximum mass for that model. M chirp 90 is again the chirp mass of the 90% of the binary black holes. So if we go to this one here, you say A90. This is our quantity of interest. We need to find out what affects it the most. So what is here is the quantity that I have seen as SS. It was the initial distribution of the mass ratio and eccentricity that was put in the code as a prescription. How do you define these initial quantities? It does not depend on what is the kick that you apply. 92% effect comes from the initial prescription that you describe. If you look at the eccentricity parameter, the most important factor is the sigma on the kick that we described here, and a bit the alpha, that is the common envelope efficiency. If you go to Mmax, it is the remnant factor. 72% of the time, it is the input parameter which decides what will be the maximum mass of the binary, not the initial factor. So essentially, if somebody says, okay, in my model, I extended the initial masses from 300 to 400, and I get a very heavy binary. So that binary will be only an outlier. It won't be produced multiple times, because we see here that initial distribution is much less contributing than the final prescription of the core collapse supernova remnant. And it is the same case for the chirp mass 90. In the bottom panel, what I show is our square value for this regression analysis that we did, and it shows for A90 99.998. What it means is that when we did this analysis, this algorithm was able to assign 99.9% of the effect of the fluctuation. Like, where is this fluctuation coming from? So fluctuation is one. It can assign every contribution of this fluctuation coming from these input parameters that we supplied. Now, the funny part is that if you look at the rows 6, 7, and 9 here, you see it's very, very low. It's almost noise contribution. Now, as I said, we have 1,000 models, but I'm showing the result for only a few of these models. So IMF, essentially, one would understand will contribute. But in our code, this parameter IMF is only called for certain values of the first parameter SS. And the models that I chose to show today, they don't have that value. So IMF is not used again and again. So even though I vary IMF, it doesn't affect the models. And this regression analysis clearly captures this thing. So essentially, IMF is not a useless model, useless input parameter. It's just that the models that I chose, it shows that it doesn't affect anything in any of these quantities, simply because it doesn't change anything. The one point to remember is when I calculated these quantities, we have not separated BBH, BNS, and SBH. These are all the binaries which were formed in the models. So the conclusions are that we generated a preliminary catalog of optically compact binaries, and this is the largest study done till date. We have parameters, we have models existing already, but not so many to us to do a full parametric studies. We identify the parameters which influence the compact binary properties. We also quantified these effects, and then when these final models are ready, they will be publicly available.
Thank you. Thank you. Thank you. Do we have any questions? Hola?
So, yeah, I'm interested in eccentric mergers, and eccentric mergers. So, you said that it is initial eccentricity of the binary, not static. So, do you assume that the tides are inefficient, or those systems are working in some exotic way without mass transfer?
Do we assume the tides are
inefficient, because normally you would expect that this extension
they would, yeah, correct. So essentially, we don't change the tidal fluctuation from model to model. It is the same in all. So I think in this code, if I'm right, the tidal interaction was not there for BBHs. So that's why it doesn't affect. If we can input it and then infer how it affects, that would be another thing to do.
Yeah.
So, I had a question. So, there are several studies which basically shows that 19/21 is can have spin precision instead of eccentricity, right? So, in this study, if we replace eccentricity with spin precision, like what kind of changes do we expect in the study?
So we are not estimating the precision now. We are not assuming the binary that form will be precise or not. That is not done in this code. The only thing is that we estimate what are spins, because that is post the formation. What we are doing is how was the compact object formed.
Yeah, please.
So I'm interested in the Paris stability. So when you mentioned, you do take that into account, right?
Yes.
What is the current status? What do we know about this? How does it affect your lack of knowledge, I guess, here? How does it affect your models?
So in multiple prescriptions, when I write this remnant, there are those prescriptions have different limits on this pair instability, and we change it that. So if you increase it, you get a massive binary. Suppose it says that it will happen later on, then
Essentially, you fix it in the code, saying that okay, if the mass cannot get lower than this or higher.
Higher than this. So if you say okay, the pair stability will only hit at 65, the code will not. Okay, so that's the thing.
It's like a hard code.
Yes, yes, yes.
Because we don't have much knowledge.
Yes.
So I have a question. You were working also on the models of neutron star black holes mergers, and but do we actually observe any neutron star black hole merger with the mass regime of intermediate mass black hole?
No,
okay.
Not yet, not yet.
Okay.
Hopefully, next detector.
Okay. Anyone here? Maybe on Zoom. Let's see. Can you check also questions?
Nothing.
Okay.
Then can I follow on this? So an SBH, right? So what is the fraction? Because I lost count the kind of GW detection. What is the fraction of an SBH events?
We have one event, no, NSBH, out of 300.
So one NSNS and one NSBH.
More. Two. NSBH, no. NSBH, no.
It's really a few. Okay, I don't see any more questions and comments. So maybe over here.
Maybe because you mentioned that there are some people claiming that this most massive merger is maybe like Earth population, but it is characterized by super high speeds to the outer screen, and if you about the origin of this star, would you expect such a high speeds?
Hierarchical merger analysis that was done, they do claim to have reproduced it, but then there is also a logic that since the estimation on the spins is already, there is a high error bar, so you cannot actually be sure that the binaries are do have such high spins, because yes, so
Maybe just one more, because like we have a few of those intermediate black holes, and I believe we can assume more or less the position on the sky. Obviously, it's not very precise, everything, but can be somehow cross-correlated with some high redshift galaxies.
Yeah, there are multiple groups which are doing this catalog fitting with the galaxy catalogs. So, but then we need more detections to do a proper cosmological study with it.
Yes, please.
I have more general questions. I'm just wondering, what's the impact of multiplicity among population distance? So, because in your simulations, yes, you're always assuming that you have a binary system.
Right.
And I'm just wondering, because I know almost nothing about population distance, but what's the impact of multiplicity on the evolution? So, is it significant or not? When you're doing this kind of, population synthesis science, yes?
So Ola might be able to answer that, but no, because did not simulate ever multiple interactions for a stellar evolution. We can talk about how, suppose a black hole is formed and there are three black holes, how they interact, but then how will they evolve as a triple, that I don't know.
Isn't it the same like in the more massive stars or stuff?
I would say like almost 100% of them are, of course, in binary, probably.
So maybe more than 100% of the population speaking.
Because maybe there are some pre-merger systems which are mastering these binaries, but they were triples or quadruples at the beginning.
Anyone wants to comment on that? Okay. If not, let's thank Neha. Thank you. Perfect. Very good. And next week we're gonna have Grzegorz Wiktorowicz talking about some X-ray predictions. So, thank you. See you in a week's time.
Thank you.
Thank you very much.
I cannot talk more.